Welcome back to ECE 442-542. We're still looking at pieces in lecture 5.2, and this is piece E, where we're relating the time to peak or the peak time to locations in the complex z-plane of a second order system. We've looked at all three of these, and the third one is what we're focusing on in this particular segment, but we've looked at settling time corresponding to circles, percent overshoot, which leads to a damping ratio going towards these logarithmic spirals, which we were calling heart shapes or hearts. And in this video, we're talking about peak time, which corresponds to angles or the shape in the z-plane that we associated with that being the wedge. Remember, time to peak for a second order underdamped system, T sub p is pi over omega sub d being the damped frequency of oscillation, and that allows us then to rewrite that relationship in terms of, or as omega sub d is equal to pi over time to peak, or as the time to peak gets smaller, omega sub d gets bigger. So the faster the system, the larger omega sub d, or the larger the damped frequency of oscillation. And remember, omega sub d actually corresponds to the imaginary component of these complex roots in the complex S-plane, where S is equal to minus sigma plus j omega sub d, and we can write that in terms of damping ratio and natural frequency, where the damping now is zeta omega sub n, and the damped frequency of oscillation, omega sub d, is associated with the vertical distance. Remember, we have this right triangle. We have sigma and we have omega sub d. If this is now our pole location in the complex plane, we now are at a distance omega sub n, or the natural frequency, away from this. Or if this sigma is now zeta omega sub n, you can use the Pythagorean theorem. Zeta omega sub n squared plus omega sub d squared is equal to omega sub n squared. And you can then find that omega sub d is equal to omega sub n square root of 1 minus zeta squared. If we plug those values in, or that parameterized form in for e to the st, now we have e to the minus sigma plus j omega sub d times t, or this is now e to the minus sigma t e to the j omega sub dt, where this particular part of the last exponential is our angle associated with the location in the complex z-plane. Here is the radius, so this is r e to the j theta sub d, and what you need to keep in mind or remember that in the z-plane, omega sub d, the angle of that location z, is now omega sub d t. This is what we need for location of angle in the z-plane. And you can now look at the corresponding lines in the S-plane, these horizontal lines corresponding to the distance up from the real line. That gives you the appropriate omega sub d value. J omega sub d1 is smaller than j omega sub d2, and so omega sub d2 corresponds to a faster system. If we are now using this relationship to connect the S-plane to the Z-plane, where theta sub d is omega sub dt, we can see that as we increase omega sub d, that's going to make this angle theta sub d larger, and that's what I'm trying to show or illustrate in these two figures shown on the left and the right of each other. That omega sub d1 is a slower system in terms of how quickly does the response peak, omega sub d1 system peaks slower than omega sub d2, and that now corresponds to, in the z-plane, a omega sub d1 gives us a theta sub d1, which is a smaller angle or a slower system. Here we have the different scenarios. This is now, whoops, I should, I guess, be consistent with my colors. Here's now theta d2, and here is theta d1, and that's the angle in the complex z-plane. So if omega sub d2 is larger than omega sub d1, I think you can see, since t is a positive number, that's our sample period, then in fact theta sub d sub 2 is bigger than theta sub d sub 1. And that's what we saw in the earlier side-by-side comparisons of those two complex planes, S-plane and Z-plane. Suppose now, let's look at a particular example. Suppose the time to peak is given in a particular number of sample periods. So this is now, let's say, the number of sample periods to peak is 6, and t is our sample period. What is theta sub d in that case? Here, theta sub d, remember, that's omega sub d t. But in terms of time to peak, that's what we started in this segment. Omega sub d can be parameterized in terms of time to peak as pi over time to peak. So now we can say, oh, omega sub d can be rewritten in terms of peak time as pi over t sub p. And that's now if I can find myself without being too heavy-handed, this is now times t, and time to peak, we've now said, is 6 sample periods. We can now replace t sub p with 6t. The t's actually cancel, and we're left then with theta sub d being equal to pi over 6. And if you're not used to thinking in terms of pi as far as an angle, pi is 180 degrees. You piece that out or divide that into 6 pieces, and you see then that theta sub d is in fact simply 30 degrees. So this is 30 degrees per sample. So as we are thinking about these poles, then theta sub d is the location of a set of complex poles, and that's now located at an angle of 30 degrees if we wanted a peak time to occur after 6 samples. And you can run through different scenarios and find different values for theta sub d depending on how quickly or slow you want that particular response to peak.